Okay, so this is problem number 10, and there we go. Okay, so it starts by asking, well, it's saying that a ball, we put some fireworks inside a ball, and this explodes. So one piece goes north, one goes east, and the other one goes to the other direction. And we don't know, we just know that that piece has twice of the mass of the other two. So we denoted the mass of the other two as m, and so here its momentum, or I guess the mass here would be two times the mass of these guys. So we know that that the other two pieces flew with a velocity of v naught, both of these. So we can express its momentum of them by saying this is v p1, this is p2, and then the other is p2 p3. Okay, after that we set it equal to 0 because of conservation of momentum. And right here we have that our momentum in the north direction just has a magnitude of v0 and v0. The the piece that goes in the east direction has a magnitude of mv0 as well. And then we know from our, our diagram here that the magnitude of the third component, the third piece, is going to be two times the mass of the other guys times its velocity, which we don't know yet. Okay, so we want to put directions to it because these are vectors. So we're going to denote the north side with the J, then the east side with an I. And this, of course, will be in the negative I direction, but we just want the magnitude of the velocity right now. Okay, so we know that the vector from north is represented by j hat, and the vector for east is represented by I hat. Okay, so if we solve by this guy right here, we move these two components to the other side. And then we divide by mass. So right here, our mass is cancelled. We're just left with the velocity and then the j and I factors. So then we know that this is going to be twice the mass, twice the velocity of this thing. So right here, our j plus our I vectors, components, is just equivalent to the square root of 2. So we can simplify that. So our velocity, or third velocity for this particle right here, would be represented by negative 1/2 of the velocity of the other two guys times the square root of 2, which this can be just simplified as the square root of 2 over 2 times v naught. And this is negative because it goes in the opposite direction. So the speed is equivalent to the absolute value of the velocity. So right here we just take the absolute value of this and we get root 2 over 2 v0. So the speed of the third component is just going to be the velocity of the other two guys times the square root of 2 divided by 2. And that's part A. So we want to find the angle, the direction of that particle as an angle from the north part. So right here we know that this is our momentum in the north, and we are just gonna have an angle in between those two. So right here we know we can draw a triangle, and our components will be, or adjacent and opposite sides are going to be the momentum of the piece that flew in the north direction, and then the momentum of the piece that flew in in this case, the west direction. So we know that it's going to be tangent. The tangent is always going to be equal to the opposite divided by the adjacent. So right here we can simplify this thing. We know that the momentum is going to be P3 and then P1 times the tangent of theta. We know that P3 is just 2 times the mass times the velocity, which we just found right here. Is going to be equal to the momentum of this guy right here, the one that blew in the north direction, which we know is just mv naught. So we divide these, and we can we know from our previous part that the velocity of this guy is going to be the square root of 2 divided by 2 times our velocity, our initial velocity for the other two pieces. So these two cancel, and we have that the tangent of theta is going to be equal to the square root of 2. And so our angle would be equal to the inverse tangent, or the arctangent of the square root of 2. So we would say that our angle, our angle in between these two is going to be equivalent to this thing. Okay, so that's basically it. Yeah.